Problem 38 in Klein's second edition organic chemistry textbook wants us to draw the enantiomers, and this is a very basic skill that we need to get familiar with. And what you can do is, if you have a molecule with wedges and dashes, change all the dashes to a wedge, change all your wedges to a dashes, and that way you don't have to worry about figuring out how to draw a mirror image. Now, if you're given a chair cyclohexane, or maybe a Fisher projection, or a Newman projection, you might have to do the mirror image. But here we just have wedges and dashes. So go ahead and copy out that six-membered ring. Change the chlorine to a wedge. Change the hydroxyl group to a dash, and change this methyl group to a wedge. And remember, if you invert any two groups, you invert the stereochemistry from R to S or S to R. So that's what we're doing. We're switching chlorine with hydrogen. Technically, there's a hydrogen there that's not shown. So we can repeat this procedure for part B. Just exactly where those groups are attached, just change the wedges to dashes and the dashes to wedges. Same thing here. Okay, don't move things around or try to figure out a reflection. You're technically reflecting up and down in front of the computer screen here. Okay, and that's what the image looks like. But it's easy just to switch all of the wedges and dashes. So let's keep doing that for part D. So this ethyl is going to switch. Okay, this hydroxyl we want to switch. And the methyl group we want to switch. Okay, and these are enantiomers. Okay, they should be non-superimposable mirror images. For E, we also have a nice six-membered ring with a whole bunch of wedges and dashes. So very easily we can just swap that chlorine to a wedge, swap this fluorine to a dash, swap this hydroxyl group to a dash, and swap out this methyl group. Me is the abbreviation for methyl. Okay, now here, be careful. Here you actually have three-dimensional stereoisomer that will switch from dash to wedge and wedge to dash, but alkenes are flat. If we were to put a mirror in front of this molecule, this chlorine on the left would indeed appear to be on a wedge in the mirror image, but the alkene, since it's flat, is still going to be exactly the same, flat, in the mirror image. But the fluorine, since it's coming out of the board, the mirror image, it would look like it's going into the board or into the mirror. So make a model if you're confused about that, but you only switch three-dimensional things, okay? sp3 hybridized carbons. Now, G here and H, we have Fisher projections. So what you want to do is, since we have no wedges or dashes, you could do some fiddling with the... I'll do a mirror image. That's what I'm going to choose to demonstrate here. There's many different ways of doing this, a couple of ways, but I'm going to put a mirror on the right and then just draw the reflection, okay? So if I do that, let's generate the backbone here of the Fisher projection. Okay. On top, we're going to have our aldehyde. Now, it doesn't matter if you technically reverse that aldehyde as it's reflected, because it doesn't matter. It's a planar sp2 hybridized carbon, right? Now, here we want to be very careful. You want the OH on the left and the H on the right, so that inverts. Hydroxyl group and hydrogen. Hydrogen's on the left. Yeah, and then OH is going to be on the right. Okay. So what we're doing is basically the same thing. We're taking two groups on the carbon and we're inverting them. We're switching their locations. So if you pop the hydrogen and hydroxyl group off and rebond them to that carbon in an opposite fashion, you'll invert that stereogenic center, and you must do that for every single stereogenic center in your molecule, like we've been doing with the wedges and dashes. So let's go ahead and do this last problem here. Let's draw our backbone out. Nothing happens to the carboxylic acid because that's not a stereogenic center, nor does anything happen to this CH2OH group down on the bottom. But we want to switch the bow ties, so to speak, of the Fisher projection and do something like that. Okay. So that's how you do this problem. I hope it helps you understand drawing enantiomers a little bit better. Oh wait, there's letter I and J I didn't see. Let's do those. So we have, these are huge molecules here. Okay, so probably a natural product, I'm not sure. But anyways, we've got all of these different stereogenic centers shown with wedges and dashes. So what we need to do is change all of the dashes to wedges and all of the wedges to dashes. So the enantiomer would be this molecule here. So this chlorine, we need to make it a dash. This methyl group, we need to make it a dash. This chlorine, a dash. This methyl group, a dash. This hydroxyl group, a dash. And I believe if you follow my method for drawing enantiomers, it's pretty foolproof. You don't have to worry about a mirror and get all confused with things. So that's 538I. Now J is a simpler molecule, thankfully. Okay, so we have this molecule here. To draw the enantiomer, we sketch out that backbone there, and then we switch the dash methyl group to a wedge, and the OH becomes a dash. All right. For letter K, we have this halogenated alcohol, and we want to draw the mirror image of this. Simply put, we just reverse the wedges and dashes. Okay, make sure you put the same atom on each of the ends of those lines. In letter L, we have another molecule. This is definitely the last one here. We have an OH group, and we have a methyl group, okay? And so for this one here, we want to, again, just invert the wedges and show them as dashes in the molecule. Okay,